Hi, welcome back. In today's video, we're going to be having a look at independence detection ID, and then in particular, it's kind of like a separate second subheading, which is going to be operator decomposition plus independence detection. So this is kind of an appendum. Independence detection is its own idea, but it's kind of appending to the last video on operator decomposition because the two of them hand in hand actually end up being a pretty performative algorithm. And all of this is kind of also within the realm of starting to look at these very simple MAPF algorithms within the realm of centralized controllers. So you have centralized A star and operator decomposition within that. So independence detection is super simple. This should hopefully be a bit of a crook one. It's really just a very, very simple way of actually detecting whether or not agents interact with each other, right? Or if two entire groups of agents are independent. So I had this problem over here before, right, where we have explicitly, in the last two videos I've been working with, Agent 1 and Agent 2 are obviously interconnected, right? Their decisions are going to be impacting each other. Whenever they try to plan their optimal path, well, they're obviously interacting. They're going to be hitting each other. There are collisions. So we would describe this as a group, right? These are a group of agents we need to kind of plan together with some form of joint space reasoning, right? But the issue with these joint space approaches is, as we've seen, the search tree grows massively, because when we treat these things as like this giant single agent with all of these like axes of degrees of freedom, well, what ends up happening is our joint plan just, it can't scale to large amounts of agents because it breaks down. We're trying to reason over too many things at the exact same time. So independence detection comes into play here and helps us dramatically, because imagine if there were other agents off in the wings in different locations that are just doing their own thing, right? If this is its goal, and then this one is maybe just going over here, wherever else, it doesn't matter. It would be really nice to be able to actually quickly identify which groups of agents we should treat as a joint space problem, right? And try to find this really tight solution together. And that's where we're getting that completeness and optimality from like centralized A star and OD. But yeah, we'd be able to identify here that there looks like there's three groups, right? This one, so agent 1 and 2 is a group. And then these other two agents are also independent groups that can just be planned immediately towards their goal by themselves. And it doesn't make sense to include them in this joint space thing because their paths were never going to interact. So that's kind of the baseline idea here. We're going to walk through in this video this large example. Unfortunately, the lightboard only has so many colors. And also the yellow, well, the yellow here, so yellow here, and orange look exactly the same. So bear with me, I'm just going to have to say the agent names, I think, often. But yes, this is a simple example where we have a bunch of agents in a shared environment. They're trying to plan their paths, and we're going to walk through and try to define for ourselves which groups are independent. So in class, this is like a tutorial activity we do. I would give students time to reason over and think about this. So please, if you're interested in having a go first, I think you absolutely should. Pause the video now for just a couple minutes and try to draw out mentally all the lines and paths, right, of the agents, and try to find for yourself which ones you think are independent. So your job here is to plan optimal paths for each agent and see whether or not they will interact with each other. So do that now. And otherwise, I'm going to continue onwards and talk through this. So we're going to start, I'll start drawing a few optimal paths for some agents. We have this agent 1 and agent 2 at the beginning that I'll deal with first. So look, the idea is obviously in grids there's a million symmetric permutations of paths they could choose. Is it this one? Is it this one? Is it this one? So forth. They can do a lot of things. Now, what's interesting though, I think, is to reason over the overlap kind of the regions for agent 1's path similarly. So we're going to have, unfortunately, a lot of permutations in between. What you might start to see is I'll start drawing X's. This is a potential collision point. This is a collision point. This is a collision point. This is a collision point. You have this entire rectangular region, right, that both agents really like and both agents want to traverse through. And so every time maybe there's a conflict there. So if you give agent 1 right of way, well then, okay, agent 2 will go, okay, well I can't go down, right, on the first time step. So I'll go 1 to the left. But then I'll try to go down. Oh, but then there's a conflict. So I'll go 1 more. I'll try to go down. Oh, there's a conflict. I'll try to go 1 more. And then even then, oh no, there's a conflict. So there's again kind of inherent in the idea of MAPF is just actually difficult. Like this idea of collisions is computationally complex because computers have to permute and iterate through all of these different variations, all of these symmetric variants. Whereas we as humans, I think, we're much quicker to intuitively realize and recognize how many conflicts we're about to encounter. Something about the way that we intuit the situation, we know this was going to be a problem. And we would already know, right, that one of the agents is going to have to wait. So part of this is let's reason over the number of moves it would take for each agent to get to their goal. So agent 1 is 1, 2, 3, 4, 5, 6, 7 away. Okay, so agent 1 needs 7 moves. Agent 2 needs 1, 2, 3, 4, 5, 6, 7, 8. Okay, so in terms of our 2 MAPF objectives, one of them is the sum of individual costs. So you would add up 7 and 8. We haven't talked about which one has to wait things yet. So you'd add up the 2 costs. Or make span, right, is the final time step. So if we're coming up with an optimal solution, we probably kind of want to optimize for both, right? Which is essentially make span in this situation. We know one of them is going to have to wait. So our 7 plus 8, one of them is going to have a +1. I think it makes sense to us humans. It doesn't matter for the problem. Let's just do it as 8 plus 8, right? So essentially what that means is the pink agent, that was 1 closer, he'll wait first, okay? So we have agent 1 will do 7 move plus 1 wait. Okay, and then agent 2 has 8 move. Okay, so that's that little problem. Note that there was no reason agent 1 is never going to go down the hallway and the other way, right? Because that's suboptimal. So when we are treating this as an independence detection problem, I have reasoned over the world. I've drawn a bunch of my paths. You don't even have to draw it, right? I think it's pretty easy as a human to see it. We're seeing that agent 1 and agent 2, they are obviously linked. They must be joined together, and we would plan them together using a centralized controller. But a centralized controller just looking at this little sub-problem off to the left of the board. The centralized controller would love to treat these other groups, as we'll talk about in a second, separately. So group 1 is obviously going to be the agent 1. I'll use the colors. Is obviously agent 1 and agent 2. Cool. Now things get a little bit more interesting though when we want to continue and start looking at the other 2 groups. Now, what I often try to get students to ask is I ask people to shout out to me the answer, how many groups do you think there are? So essentially what I'm going to get is a lot of 2 and a lot of 3. Okay, I think everyone can easily understand that this is a separate area of the map, but this now gets a bit confusing. So you obviously have this choke point here, this hallway, this corridor, whatever you want to call it, that 2 agents, or at least 2 agents, really want to go through. And then you also seem to have this other issue up here. Now, maybe I forgot to mention this at the beginning of the problem. We're working with a grid map model that means that when agents get to their target, they stay there, okay? They're not going to magically vanish. These are real-world robots. So what that means is if agent 3 walks to its goal, it will block things, right? It will block the entire hallway thereafter. So that's important. So if you want to reevaluate your viewpoint of this, again, maybe I'll give you a second to reason over this. And for those that want to continue, well, what that means then is, yeah, we're starting to see this corridor as an issue, but then also this corridor is going to be an issue. Now there's also questions, right? obviously green's always going here, but pink is 1, 2, 3, 4, 5, 6, 7 steps away, or 1, 2, 3, 4, 5, 6, 7. Okay, so in the actual algorithm, when you go to implement independence detection, it's extremely easy to implement, but you're just going to plan optimal paths for agents, and then you're going to see if they overlap with the optimal paths of other agents. It's really that simple. What that means is it depending on the way, right, you tie break and things like this, well, you could end up with different numbers of groups. So in this situation, it is completely valid, it is completely valid to have 2 groups or 3 groups. There are going to be 2 different versions of the problem here. So let's view the first world view. So imagine there were 3 groups, okay? So these would probably be, this is the case where pink has decided to go up. Now we'll see that the optimal path of pink interacts with the optimal path of green. So agent 3 and 4 here are definitely also not independent, right? They will be a group. In the case that this was the tie-breaking path, that pink chose this path, well then you would see that in this case, these 2 probably want to use the same corridor, okay? So when they want to use the same corridor, 1, 2, 3, 4, 5 steps away, that means that the agent 5 and 6 will interact. Okay, so in this case, there's 3 groups, and this is absolutely correct. So independence detection can give you different results based on tie breaking, or if you try to exhaustively enumerate everything, which I just don't think is worth it, right? It's a really simple algorithm. You're just looking for a nice little way to simplify your problem when you actually go to solve it, to just treat each thing as a little group, have your own little OD, operator decomposition controller, solving each of these sub-problems. So then there's the 2-group world. Why isn't this 3 groups is actually kind of interesting, right? So because it looks like if pink goes this way, all 3 of the optimal paths do just kind of converge into this. But what happens is essentially we have this additional step in the algorithm. So you do this initial check to see if the optimal paths overlap. In this case, yeah, you'd say that agent 4, 5, and 6 have overlapping optimal, and then 3 is in its own group. That's fine. But then what you do, you don't stop there, because you want to essentially merge groups, right? When you realize, because inevitably when you go to solve this in anything where you start resolving these conflicts, agents will look at their possible other paths. So you'll just do like a prioritized planning thing. You'll see that if the yellow agent, if the pink agent is using this hallway, well then maybe agent 5 has to wait. Agent 6, if you did the math, 1, 2, 3, 4, 5, 6, 7, 8, 9 versus waiting for 1, 2, 3, 4 plus 5, 6, 7, 8, 9. Okay, interesting. So essentially the yellow agent would have a equal path that goes up around here and would interact with the green. So you're going to merge the 2 groups together. All of that really just means if it's a 2-group solution, it'll be all of 3 plus 4 plus 5 plus 6. Okay, so all 4 of these agents on this right-hand side of the map might actually just be joined together. But hopefully this is kind of showing you the baseline idea of independence detection, and you can see how it would be really useful, right, to identify groups, and also to be able to do this thing where you merge groups and realize that even though maybe they look independent at a first view, the moment you plan alternate routes, well actually maybe you will have these larger interactions between groups. You'd be able to solve each of these, and maybe they have different effects. It's really hard to know which one would give you the best solution. And realistically, you're already gaining a benefit from this, right? We were already able to treat this as a separate group. So there'll be a bunch of tips and tricks and ways that maybe you can tune this for the exact kind of geometric topology or the kind of problem you're solving. maybe I'll just pull up on screen as well. There's this graph of results. Essentially, in these results, we see that operator decomposition paired with independence detection is actually really performative, surprisingly. So the beauty of this is that because we use independence detection, we're able to essentially separate out the search tree, and based on the based on the decomposed way that we're representing the search tree, we can really start to see that certain subtrees and things we just never need to even generate and explore at all. And we get more of an advantage compared to centralized A-star because, of course, centralized A-star has to permute through that entire state space, right? It treats all agents together. It's much easier in this decoupled approach to say that, you know, we're able to take within one node, we'll know which actions can be taken at simultaneously, yeah? If you have two different groups that don't interact, then in one single step, you can take actions in both of those groups and save massive amounts of time and computational complexity. So that's quite exciting. I won't really, well, I'll mention them here as something that maybe is also interesting for your own reading. There's also many ideas of, I'll get to them later, but the types of constraints and problems we can recognize in MAPF algorithms and name that are really useful for solving these kind of things. And we can hopefully recognize them when they happen in a MAPF problem, and instead of having to reason over and expand a ton of nodes, right? So in this hallway, for example, this corridor, we knew there was one of the agents is going to have to wait the entire length of the corridor. What's probably going to happen if you had a naive thing, like imagine prioritized planning. One agent will wait a time step, but then it will just like, oh no, sorry, it won't wait a time step because they're spawning on different. So Crisis, the whole time 6 was meant to have its goal and its location swapped in the original problem, and I just drew that incorrectly. It doesn't change anything, like all of these groups and stuff kind of happens the same. The logic I drew would have changed slightly for how the groups, I think it would have made it much easier to recognize that the two groups would merge. Anyway, point being is, okay, so if this became goal 6 and this just became 6, okay, in this worldview, right, see how they both have to go through the corridor in opposite directions? Prioritized planning would have one agent just go through, but the other agent would absolutely try to go, realize it can't, step back, and like, if the corridor was longer, imagine that, it's going to walk all the way down the corridor, then back step, and think about how many possible issues and like later conflicts and things these things can force, and also just the number of nodes you would need to expand with every possible version and symmetric variation of weighting, moving backwards, so forth, so forth. So there are these really exciting ideas. I'll draw up the names of them. Essentially, you have the idea of constraints. One of them will be, this is what we call a corridor constraint. I never remember if corridor has 2 R's or not, and if Corridor Digital, the YouTube channel, has corrupted me in some way there. This is what we call a corridor because we see how in this issue, it's going down the corridor that's the issue. So if we could recognize this from the get-go, it's really cool. We can actually simplify the problem massively by just arbitrarily issuing wait statements to one of the agents. Hey, if this agent gets to go down the corridor first, you just need to wait. Stay put. That simplifies the search problem, culls entire subtrees. That's amazing. The other issue over here we saw, there's a problem of what we call a target constraint, right? The issue is related to the target, the goal being in a choke point or in essentially the path that's necessary for another agent to reach its own goal location. So we call this one a target constraint. I think this is one of the hardest ones, but it really means you're going to have some form of coordination, right? Where you say, Agent 3, you cannot go to your target until the person that will be blocked goes through. So that's an interesting one as well. And then the last problem we saw over here, see how I've drawn up this rectangle. It's a rectangular constraint. This is the most common and I think the easiest to solve, right? But yeah, so many times when you're in this open space and two agents just simply want to pass each other, look how many possible conflicts this would actually encounter. That's crazy amount of work that we're able to reduce by doing smart things, where we would essentially create an entire constraint to block the full side length of that rectangle, which immediately tells our agent, right? So agent number 2 here will, or agent 1 technically, right? Because we said it's the one that has a shorter distance. Agent 1 will know from the get-go that this entire wall here is blocked. You cannot be in this wall at the time step or at these time steps. Therefore, from the get-go, we immediately realize that this weight move is going to be necessary. So these kind of constraint checking is really, really also an exciting idea. That's, I think, very related to this idea of independence detection, right? Because we're essentially in creating and identifying which kinds of collisions are in groups, we are also innately discussing the types of constraints, the types of problems we encounter. Okay, thank you for watching this video, and in the next video we'll have a look at CBS, conflict-based search. This is the first really, really, really important MAPF algorithm we're going to have a look at. It by itself is difficult for MAPF, but it has suboptimal versions that are constantly used and has a million family of algorithms, and these are really, really important concepts in your MAPF journey. Please join me there. Thanks.